Hi all, welcome to my ozone technology course. This will be section 22C on biofilms and biological corrosion in cooling towers. It was initially intended that we would be discussing galvanic corrosion. However, it will be addressed in section 23B. We will introduce the following: biofilms formation, bacterial biocorrosion or microbiological corrosion. Galvanic corrosion will be on 23B. This slide gives a good picture of how a biofilm is formed. As water flows through the pipe, it has quite a lot of planktons and other living organisms which will progressively stick onto the side of the pipes and cause a layer. And this layer of slime and planktons, etc., will be a site where bacteria can harbor. Generally, if you feel with the finger the side of the pipes, you will find it will be very slimy or slippery. Now, bacteria will accumulate throughout the surface of the pipe, and throughout the surface of the pipe, the slime will continue to be formed. Slime or biofilms can also be called fouling. There is a significant cost of fouling. In this chart, I obtained from Water Management Australia Proprietary Limited. It shows what is the actual energy lost, transfer energy lost because of the fouling. And the fouling is in terms of the millimeter thickness, calcium carbonate, that scales that attach to the slime, the thickness in millimeters, and the increase in energy that is required for the transfer of the heat from the refrigeration liquid to the water is higher, and therefore higher amount of energy and electricity has to be used. Biofilm, of course, you know, as is a preclude to scaling, and if that can be reduced, biofilm is reduced, then scaling will not take place. Of course, the other condition for scaling to occur is there must be a saturated solution of the calcium compounds, and the slime or plankton becomes a seeding particle. The seeding particle will cause the settling of the precipitate in a saturated solution. This slide shows where algae can be involved in slime formation, because small particles of cells of algae can also get stuck to the sides of the pipe, and that has got protective holes in which bacteria can survive, and scaling can occur. In fact, these algae particles become the fabric on which the scales will be deposited. We now will introduce the corrosion in cooling tower systems. Corrosion of the metals of the pipe, cooling coils, or chiller plates or chiller tubes, the pipes and the tanks are very serious problems that, if not controlled, will cause holes and leaks in the pipes and chiller tubes and disrupt the circulation system. Corrosion reduces the effective lifespan of the circulating system, and the pipes have to be replaced frequently and increase the maintenance costs. There are 4 forms of corrosion for our purpose. The one is called microbiological corrosion. The second is called erosion corrosion. The third is called chemical corrosion. And the fourth is the electrolytic corrosion. Each of these corrosions are discussed separately and how they are formed. All the forms of corrosion combine together and produce a total corrosion of the metal. The first we shall discuss will be the biological corrosion. It is also known as biocorrosion and is caused by extensive growth of iron and sulfur bacteria. The iron bacteria releases acids and dissolves the metal, and that is used for the metabolism of the bacteria. The sulfur bacteria metabolizes sulfates to form hydrogen sulfide, which converts to a sulfuric acid and corrode or attack the pipes and metals. The bacteria can accumulate and consolidate only when there is a biofilm or organic matter on the walls of the pipe. If the biofilm is absent, then the bacteria cannot consolidate. In this slide, there is a picture presentation as to how the slime can be a protective portion for the bacteria to accumulate, the corrosion bacteria to accumulate and produce the acids or eat away the iron. The bacteria that cause the corrosion are, for example, D-sulfovibrio, D-sulfonosulfotomaculum, or D-sulfomonas, iron-reducing bacteria, Gallionella, ferrugin, and ferrobacillus. These are the acid-producing bacteria such as Pseudomonas, Aerobacters, and Bacillus, and sulfur-oxidizing bacteria, Thiobacillus. All these bacteria are present in the cooling tower water, and in the presence of the scale, they will accumulate, consolidate, and start corroding the pipes. Of course, the scaling will add greater protection to the bacteria and will protect the bacteria from any biocides, etc., added to the water to kill the bacteria. So when biocides are added, only the water in the bacteria in the water that is flowing will be killed. But the bacteria that is below the scales, the biocide or chlorine will not reach, and therefore they will continue surviving. And as soon as the biocide or chlorine is removed, the bacteria will come back and consolidate. This slide shows the metals with bacterial corrosion. bacterial corrosion can, if this is a end pipe of a chiller, and if you notice that usually the solder joints, etc., can be attacked, which contain probably iron and other metals. And here, each of these pits indicate a colony of bacteria. So each bacteria will form a colony, will grow up to form a colony, and each colony can produce enough acid to cause pitted holes, and over a period of time these holes will penetrate out to the outer pipe and leaks will occur. As biocorrosion is very important in cooling tower systems, I have given some references that you would, if you are interested in getting to learn more about it, I've given you the following references. Please look into this and you will be able to get deeper understanding about the corrosive principles. In conclusion, in chemical water treatment, biocides, very often they are organic, are added to prevent the bacterial buildup. Corrosion inhibitors are added to reduce the corrosion. Scaling inhibitors are added to reduce the scaling. Algicides are added to reduce algal growth, and anti-foaming agents are added so that the foaming is not is reduced, and the transfer of heat can be more effective. All these chemicals together with the evaporative loss of the water increase the TDS of the water, and then when it becomes saturated with chemicals, they deposit as scales. In order to reduce the TDS, we have to do a blowdown. Blowdown is actually draining of the water of the tank to reduce the volume of the water and to drain off the saturated, much of the saturated solution, and topping up with fresh water. Of course, if you, for example, if you drain 50% of the tank and add 50% top-up water, what you would be doing is reducing a TDS by half, assuming the incoming TDS of the water is minuscule compared to the actual TDS of the saturated solution. When you add more water, you are obviously reducing the concentration of the biocides, corrosion inhibitors, scaling inhibitors, algicides, anti-foaming agents, etc. So you also have to top up these chemicals to the concentrations as specified by the manufacturers. Hence, the cost of adding all these chemicals can add up to significant costs to the maintenance of the cooling towers. We have come to the end of this session, session 22C. Thank you very much for the patience to listen to this session. The next session, 23A, will be on chemical corrosion and formation of scale and its effects on the cooling tower systems. If you are new to this session, please refer to sessions 1 and 2, which will contain the details of the course and sessions 3 to 22, which will be the course proper. If you like this presentation, please click the like icon and subscribe icon, and you will want to be, if you want to be notified of the next session. Thank you and have a good day.